Okay, it is time for the last discussion of HL chemistry on environmental impact of drugs and drug detection. All right, so brief overview of the environmental impact of drugs. So for a long time, scientists sort of ignored the impact of medical waste just because there were really bigger problems from other industries as far as environmental pollution and waste goes. But pharmacologically active compounds do present a problem. They've been shown to cause significant changes in metabolism and behavior of various organisms, including humans. And so a couple examples: release of antibiotics to the environment is a factor contributing to resistant bacteria. Other drugs can act as endocrine disruptors, which increase cancer risk and risk of reproductive disorders. Antibiotic waste, in particular, is a major problem because widespread use of antibiotics has led to antibiotic resistance. And as they're released to the environment, we're all exposed to low levels of antibiotics, so some bacteria are able to thrive and mutate. This could take place in individuals and in the environment. Antibiotics in agriculture are a really particular problem, so their use has doubled over the past 2 decades, and antibiotic use in agriculture actually accounts for 50 to 60% of total antibiotic use. And this is also the primary source of antibiotic waste in the environment because the drugs aren't completely metabolized, and so they can be excreted. And additionally, we consume antibiotics in dairy, meat, and water. So trying to address antibiotics in agriculture, the EU actually banned antibiotics as growth promoters, but the problem with that is that it didn't really work. There was no discernible effect on bacterial resistance in humans, but death and disease in animals greatly increased, and that's because decades of excessive antibiotic use have weakened the immune system of animals. So we have a pretty big problem on our hands. It's pretty well entrenched. So a couple possible solutions generally to the problem of antibiotic resistance. One would be to restrict their use to the most severe infections and be more judicious in prescribing them to humans, and also ban their non-medical use. And the second would be to reduce and then process appropriately antibacterial waste. However, for either of these things to be effective, they really have to be globally coordinated, because even if one country does these things, because we're such a global society now, if other countries aren't following through, the resistant bacteria are going to continue to thrive. Now, nuclear waste is another major source of waste, and when we talk about nuclear waste, there's really 2 types: low-level waste and high-level waste. So when we talk about medical nuclear waste, we're typically talking about low-level waste, and this has a limited environmental impact. So that means when we're disposing of medical nuclear waste, you can either dispose of it through shallow land burial, so you don't have to put it deep in a mountain, or you can burn it. And part of the reason that this is not as concerning is that a lot of the isotopes used for medical reasons have pretty short half-lives. That's what makes them useful for medical treatment. So by the time we get around to disposing of them, a lot of they're pretty far degraded. And we're also talking about small amounts. When we talk about examples of low-level waste, we're talking about things like contaminated syringes and tools, swabs, paper, protective clothing. So very small amounts with very short half-lives. High-level waste is produced in nuclear reactors. So this contains nuclear fission products and also unused nuclear fuel. So A, longer half-lives, and B, larger amounts. So high-level waste releases heat, so for several years you have to constantly cool it. Eventually you can reprocess and recycle it. Then it's vitrified, which means it's fused with glass, or immobilized in synthetic rock, encased in steel cylinders, covered with concrete, and buried deep underground. So it's quite a process to dispose of high-level waste properly, which is why it's a good thing that most medical waste is low-level. Another source of environmental contamination is solvent waste. So when we talk about solvent waste, really we're talking about the process by which drugs are produced. That's where the solvent waste is really coming from. A lot of organic solvents are toxic. Many, if not most of them, are flammable. And chlorinated solvents are a particular problem because they deplete ozone and contribute to the formation of photochemical smog. Disposal and recycling of these is a really complex process. You can oxidize them at really high temperatures, you can distill them for recycling, but either way, it's potentially costly and time-consuming. So some examples of hazardous solvents that we would want to reduce the use of would be formaldehyde, chlorinated solvents, as we already mentioned. Carbon tetrachloride would be a good example of one of those, and benzene, which is a known carcinogen. So whenever possible, in order to make this process more environmentally friendly, we would want to use a better solvent. So water is an ideal solvent. Water is obviously safe and abundant. Less ideal solvents, but still would be better than those solvents listed in the hazardous list, would be things like ethanol, propan-2-ol, which is the proper name for isopropyl alcohol. Those are still flammable, but they're not so toxic as things like formaldehyde and benzene. So whenever possible, as we try to be a little more green in the way we do things in general, and specifically as it relates to drug manufacturing, we want to pick solvents that have less of a detrimental impact on the environment. So the goal of green chemistry in general is to reduce the environmental impact by minimizing the use and generation of hazardous chemicals, which is why water is obviously the preferred solvent if possible. When we think about green chemistry, the concept of the atom economy is helpful. So it basically talks about the efficiency of any procedure as a ratio between the mass of our target product at the end and the combined masses of all the starting materials, catalysts, solvents that are used. And the more efficient a process is, the greener it is. And we also have to start finding alternatives to naturally sourced materials. So there's a couple of good examples of places where we've been able to do that and preserve the environment. So one example is Taxol, and we talked about this in the last discussion, but instead of harvesting the Taxol directly, we can use a precursor, which is much more prevalent, so it's easier to isolate so we don't have to destroy as many trees. And shikimic acid is extracted from star anise, and that process takes a full year to do the full extraction of that. And so this is an important molecule because it's a precursor for Tamiflu. And so there were worldwide shortages in a particularly bad flu year, and so they came up with a process to isolate this precursor from genetically modified E. coli. So that's another example of finding sort of a workaround so that we don't have a massive environmental impact. All right, so let's talk about drug detection. Now, when we identify unknown compounds, we've already learned / talked about several techniques that might be useful. So we talked about chromatography, and we'll talk a little bit more about that in this discussion. We've talked about HNMR, we've talked about infrared spectroscopy, we've talked about mass spectrometry, and X-ray crystallography. So all of these techniques also play a role here. So you may want to go back and review some of that from earlier so that you can answer any questions that are related. All right, so we talked briefly about extraction in the purification of Taxol. We're going to talk about liquid-liquid extraction. So this is essentially when we partition a solute between two immiscible liquids. That just means liquids that can't mix. They'll separate completely. Usually we would have one of the liquids would be water and the other would be something organic, nonpolar. And we use the solubility of the solute to separate it. So the layers are separated from each other using a separation or a separatory funnel. And we can describe this process using a partition coefficient. So the formula for a partition coefficient is that the partition coefficient of solute X is equal to the concentration of X in the organic layer, whatever that is, divided by the concentration of X in the aqueous layer. Okay? So it's just a ratio of those two concentrations. So if a particular solute is much more soluble in the organic layer, we would expect to have a high partition coefficient. If it's particularly soluble in the aqueous layer, we'd expect a low partition coefficient. This formula is not given in the data booklet, but it's just a ratio of the two, so it would probably be pretty easy to figure out on the fly. All right, so here's an example problem. So this says that we're trying to basically figure out the concentration of a steroidal hormone X. So it was extracted from 0.1 decimeters cubed of urine using 5 milliliters or centimeters cubed of hexane. So basically we have a sample, we add a little hexane, we shake it up really well, and then we can measure the concentration in the hexane layer. So what they found is that the hormone concentration in the hexane layer was 120 nanomoles per decimeter cubed. Now, we haven't really used nanomoles very much, but if you think about it, the concentration of something like a hormone is going to be very small, so it's not really surprising that we would need to do that here. So what this wants us to find is the hormone concentrations in the urine sample before and after extraction. Okay, so this is the partition coefficient, which is given in the problem. Now, we know the partition coefficient is 250, and so that's the ratio of the concentration in the organic layer to the aqueous layer. Okay, now it doesn't particularly matter what our units are here, they'll just be the same here and here, and they'll cancel out. So we can solve for the concentration in the aqueous layer after extraction. Okay, and that would be 0.48 nanomoles per decimeter cubed. And this partition coefficient tells us this is way more soluble in the organic layer than it is in the aqueous layer. Okay? Now, that's our concentration, but we want to know the concentration before extraction in the urine. So what we need to do is figure out, after we extracted it, what's the total concentration? So what's the concentration in the organic layer? What's the concentration in the aqueous layer? So we just figured out the concentration in the aqueous layer, and now we need to figure out the total moles of this hormone. So the aqueous layer was the urine, so it's 0.1 decimeter cubed. So we can multiply by 0.1 decimeters cubed to get the number of nanomoles in the aqueous layer. So there's 0.048 nanomoles. We already have the concentration in the organic layer, and so we can multiply by its volume, and we get 0.6 nanomoles. So a lot more, as you can see, in the hexane layer. So we can add those two moles together, and we get that there are a total of 0.648 nanomoles of this hormone. And so if we want to figure out the initial concentration, we had that many nanomoles in 0.1 liters. So we would get 6.5 nanomoles per decimeter cubed. This is sort of like a sort of similar process to what we did in 8.1, where we had to figure out the number of moles of acid in different samples and put them back together. So you can kind of use that to help you figure out how to process these problems. Okay, we also can use fractional distillation to separate mixtures of organic compounds. And it's helpful to be familiar with Raoult's law for this, which is given here. In Raoult's law, P sub A is the vapor pressure of A over a mixture. And that's equal to the vapor pressure of A in the pure sample plus the mole fraction of A in the mixture. So mole fraction is not something we've really worked with, but it's basically the moles of A divided by the total moles in the mixture. And there's an example on the worksheet that will work through this a little bit, but it's not too tricky. Basically, it just gives us a different vapor pressure of A over a mixture. More volatile compounds are going to have higher vapor pressures, we know this, and if we use a nice long distillation column, the more volatile compounds are going to move further upward while others are going to fall back, and eventually the most volatile compound will reach the condensation tube at the top and produce the first fraction. Okay, let's talk about drug detection in sports and forensics, because this is a really important field. So, detection of steroids in sports is most often done with mass spectrometry, and this is because we can detect them at really low concentrations this way. Now, what is more common, and we'll go into a little more depth about, is the detection of alcohol. So we can detect alcohol in one of two ways. We can use a breathalyzer or analysis of blood. A simple breathalyzer is a glass tube that's filled with acidified crystals of potassium dichromate. And you may remember this reaction from Unit 3 when we first started talking about organic reactions and the oxidation of alcohols. And you might remember that there's a color change that's observed in this reaction. So, at the anode, we have alcohol, ethanol, being oxidized to ethanoic acid. So this is the half reaction here. Now, you should be able to provide these half reactions. However, I've put in red the only two things you really need to know, because the rest of this you could come up with just by using the half reaction method to balance equations. Okay, so as long as you know that ethanol is being oxidized to ethanoic acid, that equation should be pretty easy to reproduce. At the cathode, the dichromate ion is reduced to chromium-3 ions, and again, as long as you know these two components, the rest you can just balance with the half reaction method. And then this would be the overall equation, and I just got this by multiplying each equation by a factor to cancel out electrons, and then combining them. And don't forget that since I have hydrogen ions on both sides and water on both sides, I have to combine my terms. Okay, we also have fuel cell breathalyzers, and in these, ethanol is oxidized by atmospheric oxygen on the surface of platinum electrodes. So the anode equation is exactly the same. We're still oxidizing ethanol. Oh, and one more thing I wanted to say back here. The color change here, it goes from orange to green. You should be familiar with that, and that's because the oxidation state of chromium has changed. And if you want to go a little more in depth into why the color changes, you can go back and look at Unit 2. All right, so fuel cell breathalyzers, same anode equation, but at the cathode, we're just reducing atmospheric oxygen. So the oxygen just produces water, and again, the rest of this you can come up with using the half reaction method. This is a much simpler overall equation because hydrogen ions and electrons just cancel out. So here is our overall equation. And again, you should be able to provide anode and cathode half reactions and the overall reaction. So in this fuel cell breathalyzer, there's no color change, but the electric current that's produced by the fuel cell is proportional to the ethanol concentration. So that's how they can tell how much, what someone's blood alcohol content is. You can also detect alcohol in blood using IR spectroscopy and either gas chromatography or high-performance liquid chromatography. And the infrared spectroscopy detects the carbon-hydrogen and carbon-oxygen bonds in ethanol. And basically, by comparing the absorption in the sample and the air, we can figure out the concentration of the ethanol. Using gas chromatography, we can identify ethanol based on its retention time, which is just the amount of time that it spends in the column. And to give a little more depth, when we use gas chromatography, we have to get ethanol into the gas phase. So we evaporate the ethanol and it goes into a column that contains a non-volatile liquid, so not easily evaporated. And that's our stationary or non-mobile phase, and a carrier gas, which is the mobile phase. So that carrier gas will move the evaporated ethanol through the column. The ethanol is basically constantly evaporating and condensing, which produces a narrow band of vapor and liquid. And when it exits the column, it passes through a detector. It generally produces a peak where the amount of ethanol is proportionate to the area under the peak. So this allows us to get a quantitative measure of ethanol. So we can identify the ethanol by its retention time, how long it stays in the column, because that's unique to different substances, and then we can quantify it by its peak area. High-performance liquid chromatography is pretty similar to gas chromatography, except we're not evaporating it because it's in the liquid phase. And the column has a liquid mobile phase instead of a carrier gas, and a solid or liquid stationary phase. So the components just move through the column based on their polarities and their affinities for each phase. So whether they're more attracted to the liquid in the mobile phase or whether they're more attracted to the solid or liquid in the stationary phase. Again, I always suggest plenty of reading in the textbook to supplement this video, and ask me if you have any questions.